Welcome to this course Computational Hydraulics. We are in lecture 14. In this particular lecture, I will be covering unit 10 of module number 2, finite volume method, boundary value problem. What is the learning objective for this particular unit? At the end of this unit, students will be able to derive algebraic form for a boundary value problem using finite volume method. Let us consider our general equation. In finite difference method, we have used the first term on the right hand side and source term to define the boundary value problem using partial differential equation and boundary conditions. So, let us use that for our case. Problem definition. In this case, this is our diffusion term, where this gamma, this is nothing but gamma x 0 0 gamma y. Now, this form is suited for our finite volume method, because this is written in divergence form and inside one is a vector. So, with the boundary conditions on the left and right side as Dirichlet, bottom and top side as Neumann or 0 Neumann, we can start this problem. Domain discretization is somewhat different from our finite difference approach. Finite difference case, we have considered these as nodes, but in this case we will consider cell centers for discretization of the domain. We can divide it into number of cells, and cell size in x direction and y direction we can represent it with del x and del y. This is Lx, Ly for x and y directions. These two are Dirichlet, and top and bottom ones are Neumann boundary condition. We need to have spatial treatment for corner points in this case, because for corner cell we have one side Dirichlet, other side Neumann condition. In this case, Dirichlet Neumann condition. So, let us consider the discretization of the governing equation for interior nodes. So, for interior nodes, there will be interior node P, there will be one north cell, one south cell, one west cell and east cell, with east, west, north, south these faces. Now, in finite volume method, governing equation is integrated over element volume to form the discretized equation at node point P, which is cell centered. With this one we can start, and we can use our Gauss divergence theorem on this particular problem. If you use our Gauss divergence theorem, this is our volume integral. We can write this volume integral as gamma x d phi by dx I, gamma y d phi by dy j. I j are unit vectors in x and y directions. This is corresponding to x, this is corresponding to y, So, inside one is a vector, this is written in terms of dot product. So, now with a surface integral we can reduce it, and this n is outward normal. We can further simplify it and write it in terms of phase values or phase values in this case. So, how this step is coming from this integral equation? Let us consider that we have our P phase, P cell and east phase. Now, east phase, this is normal to y direction and this is same as x direction. So, we can write the area in terms of I vector. So, area in this case is del y, and vertical perpendicular to this direction we can consider unit area or unit distance. So, with this we can write it as del y into 1, this is the magnitude of the area, and direction of the area is I. For east phase, this is the area, and for vector we have two components I and j. We need to integrate it over phase, that means all phases east, north, west, south. So, if we write it as summation, then we will be exactly solving this integral equation. So, for east phase we have del phi by del x I plus y del phi by del y j dot AXE is the area on ith direction. So, this is for phase E. Now, if we take dot product for this particular phase, then we will get gamma x del phi by del x, this is for east phase, and AXE multiplied. AXE is nothing but del y or magnitude of the area. Similarly, for this is for east direction, if we consider west direction, the outward normal is pointing towards negative x direction. So, we have used a negative sign here, and similarly we are getting only x component. For north direction we will get only y component, and south direction also with j component or y related component, but with a negative sign. In uniform grid system, we can write this east phase derivative as gamma x e, gamma evaluated at E phase, phi e minus phi p divided by del x. West phase, this is phi p minus phi w divided by del x. North phase, this is a phi n minus phi p divided by del y, and south face we have this gamma y s phi p minus phi s divided by del y. We can consider the uniform grid system where for x and y direction we have fixed values for intervals del x and del y. Now, we can utilize this for our case, and for source term we can approximate it with our approximated value at the center point into volume. Del x into del y into 1 is the volume of this particular thing. So, this is approximation of the source term. Now, we can write this compact form of the equation considering all derivatives at different phases, and we can write this with a source term, east phase, west phase, north phase and south phase. With consideration that east phase value, west phase value, this is gamma x, and y n, y s, these equal to gamma y, and x e minus x w, this is del x. We can approximate this, and we can write our governing equation simply. If we compare this thing with our original finite difference equation, then we can see that this is nothing but gamma x into phi I minus 1 j minus 2 phi I j plus phi I plus 1 j divided by del x square plus gamma y phi I j minus 1 2 phi I j plus phi I j plus 1 divided by del y square equals to minus phi x I y this or I j evaluated at I j. So, in this case we can see that there is equivalence in the finite difference and finite volume discretizations. Now, we need to consider the left boundary. Left boundary main point is that at waste phase we have specified value. So, if we consider our original equation, we need to change this derivative, otherwise we have north, south, east cells available. So, we can use our usual derivatives like our interior points. Now, for waste phase we have half distance available. So, this is phi p minus phi w divided by del x by 2. If we utilize this value in compact form, if we approximate this, this is the change. If we use this changed value, we need to transfer this phi w into right hand side because this is known. So, this is the final form of the equation for left boundary. Now, for right boundary, east face we have known value. So, derivative that we need to change is this east phase derivative. So, east phase derivative, this phi e minus phi p, this is del x by 2. Now, we can use this to get our compact form of the equation, only changes here. Now, again we can get our discretized governing equation for nodes next to right boundary like this. In this case phi e is known, so that is why it is in the right hand side. Bottom boundary we need to change we need to write this one as 0, because south face we do not have any value. So, without that derivative we can write our governing equation, and only change is here, and there is no phi s term. If we consider our top boundary, we need to eliminate the derivative at north boundary, because that is Neumann boundary condition. So, this is equal to 0. With this we can get the compact form, and in compact form you do not have the north derivative at north face. So, this is the reduced equation for nodes next to top boundary. Now, we need special treatment for corners. Let us consider the northeast corner. So, north boundary is 0 Neumann, east boundary is specified Dirichlet condition. So, we need to change this derivative, and north boundary we need to force this to this one as 0. So, with this we can write this one. Similarly, with the compact form we can get the final form of the equation. Phi e is known value. So, we have transferred it in the right hand side. Northwest corner, north boundary is 0 Neumann, W boundary this is specified. In this case we have north derivative, this is 0, this phi w this is needs to be changed, this one needs special treatment. So, with this we can change the derivative and we can get the final form of the equation. As phi w is known, so we need to write that phi w value related term on the right hand side. Southeast corner, again we have specified, this one is Neumann condition. So, 0 value for derivative at south face, for east face we have derivative available. So, in this case we need to utilize our southeast this governing equation, we will have our different discretized governing equation for southeast corner. We can see that in this case the east value is on the right hand side, the equation that is on the left hand side is phi w phi p phi w phi n. Similarly, southwest we can write our equations. In this case, south face is forced to 0 and we have only north face available, and west face value we can transfer on the right hand side. With this discretizations, we can get the interior point values and values near to our boundaries, but we cannot get the exactly boundary level values for Neumann boundary condition. In case of Dirichlet boundary condition, at boundary values are defined, but for Neumann boundary we need to use the internal values to get the value at the boundary, like our previous derivation which was for one dimensional case, and we have utilized derivative involving utilized derivative involving 3 points. First one is the node which is at the boundary, next one is the cell center which is adjacent, and next to next point is again cell center at some interior cell. So, we can get the values at the boundaries of the Neumann condition using the internal node values. So, in this case we have represented our governing equations in terms of phi p e w n s. We are utilizing single index for this one, and whatever concept we have utilized for our finite difference case, we can use those conversion techniques to single index for this problem also, and we can solve our ultimate governing equation. Thank you.